So yeah, I'm a solutions architect here at AWS. I work with companies using all 50+ services on the platform. So I'm a generalist solutions architect. And I've worked with organizations right from early stage startups, sort of VC-backed or otherwise, right up to household name enterprises. So I have a wide range of experience on the platform. More recently, I've been spending a lot of time with our machine learning and analytics services. So hopefully this afternoon, I'll give you a bit of a peek into the future and into what's in store for AWS and how that is applied to smart cities. So we're going to be going over a very brief introduction, what makes a city smart. Hopefully you've heard lots of answers to this question already today, so I won't be restating too much of that. But just framing the rest of the talk, we're then going to talk about our IoT service and what's in store from a machine learning perspective. So IoT is very much at the on the ground, how we're collecting the data and how we're representing that, and then machine learning is how do we utilize that data to the best of its ultimate use. And then there's a few examples, so doing anomaly detection, why would you care, why should we be doing anomaly detection, and then how we build machine learning services from the ground up. Just so that I can make this as useful as possible for you guys, can I get as a show of hands, who in the room would consider themselves technical? Hackers, developers? Okay, amazing. Who in the room would consider themselves a machine learning expert? Amazing, okay, so the difficult questions are coming from the gentleman there. Cool. So what makes a city smart? The short answer is data. Hopefully this is in tune with what you've heard the rest of the day, but really it's the information we're collecting about our cities that enable us to do smarter things. And increasingly it's the collection of data and the overlap of data, being able to combine different data sources to give you insights that you otherwise wouldn't be able to find. And again, we have some fantastic partners and customers working in this space, allowing you to do those overlays. But data is a moving target. Data evolves. And customers using their data and analyzing their data on the platform tend to group their activities in these sort of three categories. So the first, hopefully most people are familiar with, is collect, store, and report. So collect and store is fairly self-explanatory. We need to be able to collect the data and store it in a low-cost, durable, effective manner. And that gives us a platform to do reporting. So that might be using services like S3 or Redshift and a number of others for storing your information and giving it access to reporting tools. And this is very much review-focused. It's looking back on what has happened in the past and what can we learn from that. Increasingly, though, the applications of data are changing. So we're moving into a world where monitoring and alerting and responding in real time is becoming more important than ever. Being able to respond to events as they happen across a number of fields, but including in smart cities, being able to respond to traffic events, traffic collisions, and other critical events is important to the functioning of a city. And then looking forward, how do we use that data to predict the future? How do we move away from being purely reactive, but into a sphere where we can preempt issues before they happen and take action to prevent them? And that's really what I wanted to focus on this afternoon. How do we use the machine learning capabilities of AWS to look into the future, to look ahead to future problems so that we can start to think about how we would solve those issues before they arise? And hopefully that's of interest to the audience this afternoon. So this is a bit of an overview of all of the data services, or a large selection of the data services available to you at the moment. If you're familiar with the AWS platform, you'll be able to call a lot of these out. We've already mentioned Redshift in the center here as a data warehouse for storing your information and for analyzing it. Again, rather than going across the entire set of services, hopefully you've heard of these before and have seen some of them earlier on today. I'm going to be focusing on our artificial intelligence and machine learning services viewed down the bottom. And these are really the crux of what we're looking to do when looking into the future, but also providing new interfaces for the data, allowing people to interact with the data sources in ways other than through web apps or the traditional mechanisms we're using today. And that's where things like Lex and Poly will really come into their own. Great. So first up, I wanted to spend a bit of time talking about our IoT service, because it's fundamental to a couple of the examples I'm going to be using later on. Is anybody in the room not familiar with our IoT service? I believe there were a couple of sessions earlier on in the day, so hopefully you're very familiar. So just as a recap, the IoT service takes a lot of the undifferentiated heavy lifting out of managing your IoT devices. So it helps you generate the certificates to authenticate those devices, and it allows you to collect the messages and to route them to the back-end systems that are there to do the processing. To do this, we provide you a gateway. The gateway is the sort of single point of entry for all of your devices to publish messages and to subscribe to commands. We provide the rules engine, which allows you to determine the logic for routing these messages to the backend systems or directly into storage, example being S3. We provide you the device shadow so that you can send state commands back to your devices without them having to be connected. This is a common paradigm in IoT, but actually relatively difficult to do from a technical perspective. So the IoT gateway helps you meet that technical requirement. And then last but not least, we give you the device registry to maintain metadata about your things, where they're located, when they were last maintained, and any other aspects that might be important to looking after or deploying that thing in the real world. And so what would a message look like? Well, these can be simple. If your device is measuring a single metric, it doesn't need to have a complicated message structure. So what we're looking at here is a JSON formatted object with latitudes, longitudes, elevations, and headings. And this may be a car, for example, the IoT gateway connected to a set of sensors in a car. And these messages allow us to do some very complex things on the back end, despite being very, very simple to collect and to represent. One example that I wanted to call out very quickly, and again, we'll take a look at anomaly detection in more detail, but being able to collect this information and to view it in its time series form allows us to look for anomalies, look for things that are out of the norm. And this becomes fundamental for reporting. But again, as I said, we'd like to focus on looking into the future. Anomaly detection is something we can currently do. It's something that's actually relatively straightforward, particularly with Kinesis and Kinesis Analytics. But I wanted to call it out as an obvious use case for collecting these streams from the IoT service and what insight we can get straight out of the gate. So straight on to our machine learning service. It's great that there's developers in the room, but as we saw, we only have one individual who would consider themselves a machine learning expert, and that's actually fairly representative. So the machine learning service from Amazon is designed to make it as easy as possible to get started with machine learning. It makes it simple to upload data, to train a model, and to push that model into production where it can be used with other applications. It really lowers that barrier of entry for everyday developers. And when you combine that with IoT information, we can get some phenomenal results. One of the precursors to machine learning is that we have data to train models on. And what IoT allows us to do is to collect vast sums of real-world data, real metrics from working systems. And so when we start to combine those in the context of smart cities, we open up some very, very interesting capabilities and prospects. And this goes beyond simple automation. At the moment, we have the ability to automate systems to change the way traffic lights are running, for example, or to reschedule things in real time. But this is very much kind of pre-computed. Humans have designed the responses they would like, and they've turned them into automated processes. They aren't dynamic. They don't change. They don't respond to real-world events. So we don't just want pre-computed or developed robots changing our systems. What we'd really like to get to is a system that learns and can take action intelligently without human intervention. So examples of this might be traffic. I think traffic reduction is a big topic, particularly here in London, and even more so with some of the rail and other issues that we've had recently. How do we reduce traffic and improve the flow of traffic through our cities? And so really with IoT devices, and the example that we showed with our IoT service collecting information from cars, what I'd like to show you is how we can use that data to predict and categorize car actions to help the overall system. So from our example earlier, we're collecting a timestamp from a particular vehicle. So we've got the timestamp and the vehicle ID. We've also got the latitude, longitude, elevation, and direction. What we might also be collecting, or might be available through an open data program, is the traffic light information. What signals the traffic lights we're showing and where those traffic lights are. And what we'd like to do is to attach behavior models to this data, be able to determine what a car is supposed to be doing or what a car is doing, so that we can detect anomalies and so that we can find issues when they're happening and maybe even predict issues further down in the future. And these are two examples of expected behaviors. So we expect that cars are going to stop at red lights. We hope that that's the case. We expect the cars are going to be able to turning left and right. We expect that they will be able to park up. And again, we hope that they're parking in responsible places. And unexpected behaviors, examples that we can come up with straight out of the gate, is cars that are stopped in the middle of the road for long periods of time. That usually indicates a problem. Erratic driving, so cars driving on the wrong side of the road or misbehaving generally. And overflow or floods of messages that we weren't expecting to get. All of a sudden, we've got thousands more cars than we've expected or experienced in the past. That's an indication that something is wrong with the system. And so what does this look like in a data representation? So this is an example of tabular data containing a series of these events. So we've got our exactly the same latitude, longitude, elevation, heading, and what we're trying to predict or what we're trying to determine is the target column, the activity that that car is doing. So how do we go about doing this? Well, in the machine learning world, there's a split in approach between supervised and unsupervised learning. Hopefully that isn't completely new, but for those who aren't familiar with machine learning in depth, supervised learning is where you give a machine learning algorithm examples of past behaviors. So these are the correct answers. These are the behaviors that we've seen and that we've tagged beforehand. We want you to find similar examples of that. Unsupervised learning is giving a machine learning algorithm the raw data and asking it to infer any patterns or behaviors that it can. And these are used for different use cases. Today we're going to show examples of both, how you might use supervised and unsupervised learning. In some cases, the prerequisite of needing tag data for doing supervised learning is restricting. Finding those tag data sets can be difficult, or actually going through and manually tagging them can also be challenging. And again, we have a set of services to help with that. So for those of you who are interested and haven't come across Mechanical Turk, Mechanical Turk is a platform on AWS that allows you to field out human intelligence jobs to human workers. A great example of this is tagging images. So if you had CCTV or road traffic information and you wanted to tag cars that were misbehaving, for example, Mechanical Turk would allow you to field out those images to real people to allow them to determine whether the car is broken down, whether he's driving on the wrong side of the road, or any of the activities that we're looking to do. So it is entirely possible to use the AWS platform to help with that tagging, but we're also going to go over some unsupervised methods to show you how, in the real world, you might go about working around the tagging problem. And so what we're aiming to do is to give this data set up to the Amazon Machine Learning Service and allow it to build, or help us to build a model to predict or to categorize those activities given future data points that don't have a valid activity. So that's cars driving after we've deployed the machine learning model to determine what they're actually up to on the roads. And what this would actually look like is we pass up our data set to the machine learning service. The machine learning service walks us through creating a model, including tuning and parameterizing. So we would be able to see the outcome of our model on predicted data sets. Usually this is done in a sort of 70-30 or 80-20 manner. We reserve 20% of the original data sets to test the model thereafter. So we train on 80% and then we test our outputs on the remaining 20% of the data to determine how accurate our model is overall. So the machine learning service helps you do that. It also gives you a very graphical interface for doing the tuning. So you can balance false positives and false negatives by tuning the parameters in real time. And once we've got our model, the machine learning service allows us to generate an API from that model that we can immediately use to pass new information to do real-time predictions or categorizations based on that model. This, again, is a very common challenge in data systems, particularly with data scientists who have great depth of knowledge in building models, but maybe less experience in infrastructure and deployment, pushing a model into production is a challenging task. And the machine learning service simplifies that for you by turning your model into an API that you can immediately start to query. Again, from a developer's perspective, not having to worry about taking the model and deploying it onto infrastructure behind an API and dealing with the complexity of authentication, authorization, and all of the other challenges that come with managing APIs is a huge capability that the service gives you out of the box. And what that would allow us to do is take a new metric, a new observation, so our latitude, longitude, elevation, direction, pass it to that API generated by the Amazon Machine Learning Service to give us a likelihood of that behavior being one of the ones that we're looking for. So in this case, the observation that we pass to the service is 90% likely to be a car parking, which is fantastic. We've now got a mechanism for determining a car's behavior from past observations using the machine learning service. What happens when we pass an observation to the machine learning service and it doesn't come back with a likely solution? Well, this again goes back to anomaly detection. If we can't determine with any certainty what that car is actually doing, that we can consider an anomaly. And we can flag that up for somebody to investigate. So not only have we got the ability to determine what a car is doing from past behaviors using machine learning, but we now have a mechanism to find out when cars aren't doing things that we've expected them to do. And we can do a number of things with that information. We can, as I said, alert and report on that, but we can also use it to improve our model. If this is a valid maneuver for a car to be doing, we just haven't sort of thought about it beforehand, then we can add that into our model to improve it for the next iteration. So how do we build the training data? How do we get this data set that I've neatly presented to you up on the screen? Well, using the rules engine in the IoT service, it's trivial. This is an example rule for grabbing all of the actions from our My IoT app /cars and pushing it into a bucket in S3. This will store those observations in flat file format in S3 that we can directly use to load into the machine learning service. So really at the core of the tenet of the IoT service, taking that undifferentiated heavy lifting out of managing your IoT infrastructures. So we move on then to unsupervised learning. How do we use techniques in the machine learning space to determine these behaviors without having to tag them beforehand? So the example I'm going to use here is clustering. Clustering isn't the only mechanism used to determine these behaviors, but it's a common one that we see with customers. This isn't built into the Amazon Machine Learning Service, but there are reference use cases and tutorials on how to do this on top of EMR in the Spark and the Hadoop ecosystems, as well as in RStudio on top of EC2. So if you're interested in doing clustering and you haven't done it before, then by all means come and find me after the talk. But what is clustering useful for? Why are people doing clustering? Well ultimately, clustering allows you to determine clusters of behaviors. So we take our original data set that is untagged, that we don't have the tagging behaviors for. We pass that into a clustering algorithm, and it will try and identify clusters of behaviors that we can then inspect ourselves and apply tags to. And what this would allow us to do is to determine our observations in their clusters and then manually tag those with their behaviors. So the arbitrary tags that our clustering algorithm has given us are sort of A, B, C, D, E, F, G. We can then have a look at those and determine which behaviors we've identified that a car should be doing, for example, that we can attach to those clusters. And that allows us to tag our data set without having to have humans have a look at these behaviors beforehand and tag large data sets to use for the machine learning process. And again, we now have the capability to take a set of observations, clustered, tagged, and passed into the machine learning service that we can then use to categorize these events with new events as they arrive. It also allows us to do the anomaly detection, as we were doing before. So why do we care about anomalies? Well, usually anomalies, as I mentioned, represent activities that we weren't expecting. these could be a number of things. It could be malfunction, so cars breaking down. They're not in a parking state because they're in the middle of the road. We want to investigate that. But it could be new extensions of the existing model, things that cars should be doing that we hadn't thought about, but also intrusion, malware, or attacks. This may be somebody pushing fake events into our pipeline, interfering with our overall operations. And so anomalies are worth having a look at for more than just improving the model. And getting these anomalies out and being able to detect anomalies also allows us to take action on them. So a prime example here would be if we have detected an anomaly, if there is a particular device that has been compromised and is sending us erroneous data, we can revoke its certificate using the IoT service. We can stop that device or the individuals or the set of devices masquerading as that individual car or IoT device, and we can remove it from the system, which gives us a capability to protect ourselves in the event of attacks. And that's just one example of what you might like to do with an anomaly that you've detected. So really, anomalies are symptoms of problems in the underlying infrastructure. And using these anomalies and paying attention to anomalies allows us to evolve the overall system. And these are techniques that are important not just in the IoT and machine learning space, but all applications. And so we use anomaly detection to set up the guide rails and to set up the processes for defending the system, again, using machine learning to determine those anomalies. So hopefully I've given you a bit of a peek into what it takes to build machine learning algorithms, but also how straightforward it is using the Amazon machine learning platform. And just to reiterate, we went through the 6 steps that you would need to do to get a similar model built. So we did a bit of cluster analysis. We used the output of those clusters to build a predictive model. We ran predictions in real time using the APIs generated by the machine learning service. We then came up with a set of strategies for handling critical risks, for doing anomaly detection, and then the actions that we might look to take when those anomalies arose. We assessed them, and then we iterated. Yeah. Cool. So I've spoken about our machine learning service and how it makes it easy for developers to get started with machine learning, but I wanted to call out a couple of the other services we announced fairly recently and were certainly big news at reInvent towards the end of last year. And those are starting with Poly. So Poly is a service to create human or lifelike speech from text. And what Poly enables you to do is create applications with voice interfaces. You can think of this as a great way to interact with devices in cars. You would like hands-free kinds of interactions. Poly allows you to turn text into speech, so humans don't have to concentrate on side screens or heads-up displays to interface with the notifications that you're generating from your traffic data. From an accessibility perspective, Poly is a wonderful service for helping users who otherwise would be vulnerable on our roads and in our cities. Using Poly, you're able to do as you will with the audio that's created. So caching is entirely possible. If you'd like to keep the audio snippets that are generated from Poly to reuse in your application, it's entirely available for you to do that. And otherwise, it is consistently fast responding for real-time voice-enabled applications. So if you haven't seen Poly, I'd recommend you take a look at it. The audio snippets are amazing. We do a set of languages and a set of accents within languages, and they certainly can be good fun to play with if you're just a little bit interested. So the next service we have is Rekognition. And what Rekognition allows you to do is several things. First is in the tagging of images. So if you do have users uploading images, or if you're trying to collect tags of user-uploaded images, the Rekognition service will use its deep neural network model that we have trained from example images to tag those images for you. So it can pull out things like a bicycle in an image, or give you some general tags for a scenescape, for example, pulling out a beach or a city. So Rekognition allows you to find out what your users are looking at. Examples of this might be the heads-up display in a car. So if you are taking video from the front of a car and a bicycle's in front of it, Rekognition would detect the bicycle, certainly in that case, it's a very bad day for the bicycle, but it's an example of using Rekognition to get the information about what is in the images for you to use elsewhere in your application. So it's kind of image to text translation in the rawest form. What Rekognition also allows you to do, if you have a facial database, is to do comparisons. So if you have uploaded, you already have pictures of, for example, users in a security system, Rekognition can calculate the similarity between two human images, between two facial images. And so again, the service can be used for authorization, authentication, and in smart city use cases can be used as a form of identity. And last but not least, Lex. So Lex is still in preview. It's not generally available yet, but what Lex will allow you to do is to build conversational interfaces for your applications. And again, this is using machine learning techniques in the background to help you build chatbots or, again, if you're using text-to-speech capabilities, actual interfaces for your applications for people to have real conversations with. And again, we're using natural language understanding under the hood to recognize the intent of the text, the intent of what somebody is asking of your chatbot or your speech-enabled application. We're passing that back in a format that your application can understand. You're then free to use intents or sort of lookups or constructs in your applications to deal with those intents and return the answers. So Lex makes it really, really straightforward for getting those chatbots or those talking applications in the hands of your users as quickly as possible. So yeah, we're coming up to 5 minutes to 4, so I may be able to give you 4 minutes of your time back. The last thing I wanted to call out was a few of our partner solutions. So if any of these are unfamiliar to you, do take a look. Some very, very cool use cases with AWS services in the sphere of smart cities. And without further ado, that's it from me.